But yesterday we took those basic properties of those exponential functions of y equals b to the x or c to the x, and we transformed them by vertical stretches and or reflections, horizontal stretches and or reflections, and horizontal and vertical translations to determine properties of new functions. We also continued to expand on our skills analyzing applications of exponential functions, where we finally got to the point where we changed y equals c to the x, which is what we talk about in your textbook, to this little beast, which is on your formula sheet, and it can be used for any type of exponential growth or decay. Do me a favor, take a look at your work in this section. Does anybody have any questions you would like me to go over? Shazmaida? 4? So without using technology, match each graph with a particular equation. So before I look at the equations, what are some differences between these 4 graphs? Well, one of the differences is 2 of them, they all have horizontal asymptotes, but 2 of them have horizontal asymptotes that are below the function and 2 have horizontal asymptotes that are above the function. In other words, in graphs B and D, the range is y is greater than or equal to the horizontal asymptote. And without worrying about the precise nature of the exponential function in terms of the base, exponential functions, generally speaking, before they're translated, generally speaking, exponential functions either look like that, if they are increasing, or look like that if they are decreasing. So, a couple of things I want you to note about these 2 exponential functions. Even if they are stretched, this is A, and in both of these, A must be positive. Now I realize that that y-intercept is not necessarily going to be that number if I start moving things around. But the point is, if the graph is above the horizontal asymptote, it started off with a positive vertical stretch. And what that tells us is that this must have a positive value of A, and this must have a positive value of A. Does that make sense so far? Okay. Whereas, I'm not going to redraw these, but if A were negative, these 2 green graphs would be flipped across the x-axis before any other changes occurred. So this must be A is negative, and this must be A is negative. The other very useful thing in knowing, and again, I'm purposefully not looking at the choices because I want to teach this to you in a general way, is that wherever the horizontal asymptote lies will be the value of k. Because k is the vertical translation, and the vertical translation, everybody, is the only thing that can move the horizontal asymptote. So now what we can start to do is, well, get some answers. First of all, we have 2 values of k that are unique, meaning I have a value of k in graph B that's -2, and none of the other graphs have a k of -2. So I can immediately match graph B. I hate that they have A, B, C, D here and the graphs are A, B, C, D, but that's okay. We can immediately connect graph B with this. Because it's the only one that has a horizontal asymptote at -2. You will notice, by the way, that the value of A is positive. There's a +1 in front of that graph, in front of that function, and that explains why this graph is moving above the asymptote. We can immediately say that graph D must be this one because it's the only one with a horizontal asymptote at 1. Its k value is 1. The other two we can't really do anything with here. We see there's a negative in front of both, and this is very tricky. So I want to spend just an extra minute on this. With graph C, you have, this is for C, capital C. For graph C, you have this. And for graph D, you have this. A lot of 2's and 1's. The thing I want to impress on you is the base here is a half, but the base here is 4. Which, by the way, as long as there aren't any horizontal reflections, means that D, the equation in D, has to have a graph that would be an increasing function before it's reflected. So if you take a look at this graph right here, graph C, again, I hate that it's ABCD, ABCD. This would have been increasing, and then it's reflected, so this must be the one that has a base of 4. And, and then that leaves the third graph, graph A, must match choice C. I don't think it's necessary to analyze every feature of each of these 4 graphs and match it to every feature of each of the 4 equations. I think what's important is you can use logic to say this graph must be this equation, these 2 graphs are between these 2 equations, and use logic to nail down which graph goes with which equation. Is that helpful at all? Okay. Any other questions? Yes, Arden. 7D. So describe the transformations that are necessary in order to produce a new function from y equals 4 to the x. Now, well, there's 2 parts to this. We have to describe the transformations, and then we have to write the equation. So I'll just run through the descriptions. But first of all, before I get to the descriptions, it's worth our time to identify the values of a, b, h, and k. K is -5. And, all I'm doing here, Arden, is I'm comparing this to what's on my formula sheet. This is all I'm doing for the first part of this question, to identify a, b, h, and k. So a is equal to 2. B is -1/3. H is +1 because it's x minus 1, and we compare that to x minus h, and k is -5. Are you okay with that first layer of this? Okay. So, and I hope you're okay as well. I'm not going to write out the transformations. I'm going to verbally describe them. If a is 2, then there is a vertical stretch by a factor of 2. If b is -1/3, then there is a horizontal reflection across the y-axis, and there is also a horizontal stretch by a factor of 3. If h is 1, the resulting graph is then shifted 1 to the right, and since k is -5, it's shifted 5 down. Now, if you want to determine the equation, we go back to the meaning of function notation here. Let me write down what the function is. The function is f of x equals 4 to the x. So this part right here is f of, well, I'm going to look up here actually. Let me move some things around. Whether I look at the question or the template, I guess it doesn't matter. What this means is that whatever b times brackets x minus h is, x is replaced with. So what I'm going to have for this new function will be a 4 raised to the b times x minus h, negative 1/2 x minus 1. That function is going to be multiplied by a, which is 2, and then we're going to add k, which is negative 5. Is that helpful? Perfect. Any other questions before we get started today? All right, then, if you can do me a favor, please, and open up your note package to page 8 of your unit handout. We can get started with lesson 7.3. What we're going to be doing today is solving exponential equations. We're going to solve exponential equations in a number of ways. At least one of the methods we're going to use today to solve an exponential equation is being used because you don't know how to solve certain ones algebraically. But there will come a time where we will have to solve all exponential equations algebraically, and that time will happen after we learn about a thing called a logarithm. So we are solving exponential equations algebraically if the bases can be expressed with a common base. If you have an exponential equation, and I know that you probably don't really get what I mean here by a common base yet, but if you cannot express everything in the equation with the same base, then you cannot solve it algebraically today. But you will be able to solve it algebraically next week. And then equations that we cannot solve algebraically, because we cannot put the bases as being the same, we have to solve graphically. And we're going to continue to look at a specific type of exponential growth today called compound interest. So to begin with, an equation like 2 to the x equals 32 is called an exponential equation for a very simple reason. The thing you're trying to find, x, is in the exponent. You're trying to find the value of part of an exponent, and that's what makes it exponential. So the first set of examples is going to illustrate one method that can be used to solve these. The first equation is childlike in its simplicity. 7 raised to the 4x minus 5 equals 7 raised to the 2x plus 3. Well, to solve this, and we're using logic here, we're not performing an algebraic operation. To solve this, we're saying if 7 raised to a particular thing is equal to 7 raised to an apparently different looking thing, the only way those two things can be equal is if the exponents are equal. I mean, just to give you an illustration here, and I don't want to go with the 7 because the numbers won't match with this question. If I told you 9 to the 8 equals 9 to the x, and I said to you, what is the value of x? Well, x has to be 8, doesn't it? That's the only way they're going to be equal. If I told you, this would be x equals 8. If I told you, on the other hand, 9 to the 8 equals 9 to the 2x, what would x have to be? Well, it has to be a number that will give you the same exponent of 8, which would mean here x would be 4. So when we go, this is really important for a written response, when you go from this equation to this statement, you are not dividing both sides by 3. You are not canceling the 7s in any way. It's just a comparison, that's all. And what we've done is turned this equation, which is a Math 30 equation, although I think this is too simple to be on an exam, we've turned it into a grade 6 or a grade 5 question. You know, maybe they haven't studied formal algebra yet, but they could solve this if you explained what that means. What we would do here is we would subtract 2x from both sides. I'm just writing it this time. You know I don't normally write this because I'm going to get 2x minus 5 equals 3. And you might wonder why I have 2x there. It's because 4x minus 2x is 2x. No. The question is, can we use a system of equations? And I'm just going to answer no to begin with by saying it's not a system, it's one equation. And what you're thinking is, so what I'm going to put here is not what you would do. I understand what your thinking is here, and you're saying I want to get rid of the x's somehow, right? But if you do this, there's a huge flaw in that. And then you've multiplied one side of an equation by 2, but you haven't multiplied the other side by 2. By the way, if you follow that through, and you're not allowed to do this, but if you follow that through, you're going to get 4x minus 5 equals 4x plus 6, right? If you subtract 4x from both sides, mission accomplished, you've got rid of the x's, but look at what you're left with. You're left with a statement that's just false. So you cannot do that. Yeah. If you had 4x minus 5 equals a number, and you had 2x plus 3 equals a number, so you had two separate equations, then that's what the route you would go, or you could go. But if you had 4x minus 5 equals a number, you'd just rearrange for x anyway. I'm going to add 5 to both sides and get 2x equals 8. So you get x equals 4. And there's really no need to check exponential equations yet. There will be some where we have to check for extraneous roots later. But if you check the left side and the right side here, we had 7 to the 4 times, we got x equals 4 minus 5. And the right side is 7 to the 2 times x, we got 4 plus 3. 4 times 4 is 16 minus 5 is 11. So you get 7 to the 11. 2 times 4 is 8 plus 3 is 11. You get 7 to the 11, so it checks out. You don't have to check any of these. I mean, there's going to always be exceptions, and when we bump into them, I'll talk about them. 3 raised to the 3x plus 1 equals 81. So we have two bases. We have a base 3, and we also have a base 81. I know you may not look at this as a base, but it is, because 81 is 81 to the 1. 81 is a base in this equation. The question is there a number that both of these bases can be expressed as for a new base? I hope what I'm about to say is clear. Since 3 is the smaller number, we would ask ourselves if we can write the bigger number as 3 raised to it, rather than trying to write, listen to this, I don't think we want to try to write 3 as 81 raised to a number, do we? But we want to see if 81 is a power of the exponent 3. And how many of you know what it is? It's 4, right? And you might have to play around with your calculator, but if you have to, you have to. You can't just sit there and hope it's going to pop into your head. You have to go, well, is it 3 squared? Is it 3 cubed? Is it 3 to the 4? And what we discover is that 81 is 3 to the 4. So now what we have is a common base. You can write the 81 as 3 to the 4. The 3 is already a base of 3. So this equation now becomes 3 raised to the 3x plus 1 equals 3 raised to the 4. And again, really simple so far, not really an exam question, just kind of warming up to more complicated things. Now that the bases are the same, again, here's the logic. If the base on the left and the base on the right are equal, and the left and the right side are equal to each other, then the exponents have to be equal as well. It's just a logical conclusion. So you get 3x plus 1 equals 4. Subtract 3 from both sides, and subtract 1 from both sides to get 3x equals 3. Divide both sides by 3, and you get x equals 1. And you can verify, I think, just by looking that if you were to put 1 in for x, the exponent on the 3 on the left would be 3 times 1 plus 1, which is 4. Okay, 36 raised to the 2 minus 3x equals 216 raised to the x. So your job right now, and I'm going to give you a minute to do so, is to find out how you can write these two numbers so that they each have the same base. Of course, they will be raised to most likely different things. Well, they have to be because they're different numbers, right? Can you do me a favor, please? Put your hand up and then down once you've got it. See, my thinking, this is my logic, is maybe it's like the previous one. Maybe 36 squared is 216. I mean, I happen to know it isn't, but maybe I can write 216 as 36 squared, in which case the common base is 36. But I square 36, and I don't know what I get, but I get a pretty big number. Right? I mean, I get over 1,000, I would guess. So then I go, well, I'm going to focus on the smaller number. I'm going to focus on 36. I'm not going to try to rack my brain around how I can write 216. How can I write 36 as a power? Well, I can write it as 6 squared, and that's it. That's all I can do with 36. I can write it as 36 to the 1, or I can write it as 6 squared. So if 36 is 6 squared, then is 216 also a power of 6? And, you know, this is where you go to your calculator, and after a little bit of work in this unit, you're going to become more familiar with some of these numbers. 6 cubed is 216, isn't it? So we use our calculator to confirm that we have a common base. Now watch very carefully of how I do the substitution here. This 36 is going to be written as 6 squared, and it's in brackets, and it's raised to the 2 minus 3x. That's how it must be written. This is equal to now 216, which is 6 cubed, and that is raised to the x. And now what we need to do is go back to, well, grade 9, grade 10, grade 11. You talk about these exponent laws quite often. When you have, say, x squared cubed, that's equal to x to the 6. This is what is typically called a power of a power. It's actually an exponent of a power, but it doesn't really matter. The reason this works, that you multiply these two exponents, is x squared cubed means x squared times itself 3 times. And that means x times x times x times x times x times x. So you get 6 x's being multiplied together. So our next step here, since a power of a power, and if you like, I can write this in an even more general sense. Our next step is to write 6 raised to the 2 times 2 minus 3x equals 6 raised to the 3 times x. Now, a couple of things. How many of you would have just written here at this point 6 raised to the 4 minus 6x, potentially? That's fine. You can do that. But on a written response, you need to show that you're multiplying. So you don't want to skip this step on a written response. How many of you might have just written that? Just from here in one fell swoop done that. If you do that, you will not get full marks on an exam. You need to show what you're doing to the exponents and then drop the bases. So what I am showing you here, you need to show. Well, I'm going to write this as 2 times 2 minus 3x equals 3x. You don't actually need to write this line. You could multiply that 2 by the 2 minus 3x as you're writing it down. But anyway, what are we going to get? 4 minus 6x equals 3x. And now we can solve this equation. Again, you've heard me say this lots of times, numerous times. I'm a huge fan of changing complicated problems into easier problems in math. This is a grade 7 question. So I add 6x to both sides and get 9x equals 4. I divide both sides by 9 and get x equals 4 over 9. That's it. Any questions with that one? Okay, one more. 5 to the x equals 625 root 5. Well, if we're, you're not going to know this if it's on an exam, but it's in this lesson on common bases. If we're expected to solve this equation using common bases, then apparently everything can be written with the same base. And since we have on the left-hand side, 5 to the x, that common base must be 5. It has to be 5. Because you can't write 5 any other way. It's not 2 squared or 2 cubed or 3 to the 5. It's 5 to the 1. So the question becomes, how can we write 625 as a power of the base 5? How can we write root 5 as a power of the base 5? So you use your calculator for the 625. I want to say 4. 5 to the 4 gives you 625, so we can put a 4 here. This, we're not really going to use our calculator. We have to use our knowledge of square roots from Math 20-1, which says that an exponent of 1/2 on a base is identical to square rooting something. And in a very general sense, the nth root of a base is x raised to the 1 over n. And this is a grade 11 idea that you were taught. We'll get back to the question in a second, but it's why on my calculator, if I ever want to take the square root of 75, very often you will see me do this. Because that means a square root. 0.5 is a half. Just to confirm that, if I take the square root of 75 with the square root function, I get the same number. So what we're going to do is rewrite this equation as 5 to the x is equal to, let me scroll up to see what we had. 625 is 5 raised to the 4. Root 5 is 5 raised to the half. Now what we have to do, so we're relying a lot on our exponent laws, is we have to use the idea that if I had, well, I'll just pick numbers, p squared times p to the 3, that's p to the 5. We add the exponents. And I think if I gave you p squared times p cubed and I said, what is it? Everybody would say p to the 5. But if I gave you, I'm not going to use 3. If I gave you 4 squared times 4 cubed, a lot of people will think it's 16 to the 5. Because you see numbers there and your brain wants to multiply those numbers, but it's not. It's 4 to the 5. The base stays the same when you multiply common bases. So all we're going to do here for our next step is write 5 to the x equals 5 to the 4 plus 1/2, which means x equals 4 plus 1/2. And you will see that the questions get more complicated than this in your practice. But anyway, 4 plus 1/2 is 4.5 or 9 over 2. So x is 9 over 2. Any questions with that example? All right. So what if we had something like this? 25.8 equals 3 to the x. You cannot express 25.8 as a power of 3. Well, you can, but you don't know how, because you need logarithms. So first of all, your textbook talks about this in the program of studies, the curriculum, the course expectations talk about this. I'm going to show it to you, but it's really clunky. Clunky means awkward. What you do here, and I'm not going to show any work, is you take a guess. Let's say 3. Well, I know 3 squared is 9, right? And 3 cubed is 3 times 3 times 3, which is 27. Which means that if 3 squared gives you 9 and 3 cubed gives you 27, 25.8 will be arrived at by taking 3 to some number between 2 and 3. And again, I don't like this method. I think it's really weird. I'm going to go 2.8. 3 raised to the 2.8. No. 3 raised to the 2.9. No. 3 raised to the 2.95. You get the idea here? And, I guess what we could do is put in for y 3 raised to the x. Set our table up to be on ask. Go into our table and start plopping in 2.95, 2.96. Oh, 2.96 gives us a little bit too much. Let's try 2.955. Do you get what's going on here? It's a simple process, but it's just time consuming. So maybe 2.956, 2.957, 2.958, 2.959. That's pretty close. It's somewhere between, and I just want to show this to you. Since these two numbers are on both sides of 25.8, x must be between these two numbers. So you can put down 2.96. In reality, it's actually this number. You don't need to know how I got it, and how I got it is not, in fact, how you're going to get it later, but this is the number. Okay, and we will learn how to find the exact value later. Let's try another one. 12 to the 12 equals 1.5 to the x minus 8. I would fully use the capabilities of my calculator. I would put in for y1 1.5 raised to brackets x minus 8. I would go to my table, and I've got it set to ask, so maybe you want to put it on automatic first. Start at 0 and go up by 1. I want this to be 12. To how many of you does it kind of make sense that x must be a pretty big number? because it's 1.5 raised to x minus 8. We want to get 12 out of that. So I got to raise 1.5 to a pretty big number to get 12. And to boot, I'm taking 8 away from x before I'm applying that power. So looking up here, I see that it's somewhere between 14 and 15. Again, I want this to be equal to 12. This is my y1. That y1 is a little bit less than 12, and then it's more than 12. When x is between 14 and 15, then that's when we can get 12 out of it. So now, I mean, maybe you want to do this. Maybe what you want to do is set up your table to start at 14 and go up by 1 to try to narrow it down. I know I had that in there, but when I go in there, all it just confirms is it's between 14 and 15, but now I can narrow it down more. Let's go up by 0.2, or whatever number you want. And I go in here and I see that, oh, there's 12. It's around 14.2, and I play around with it some more. Now what I might do is set this up to be on ask. I think I said 14.2. That's a little too much, so let's go 14.1. That's not enough. Let's go 14.15. Do you get the drift here? It's not something I think you're going to want to do. But who knows, on a diploma exam, it might give you, Peppermint Patty solves the following by systematic trial and error. And you need to understand what it means. To 1 decimal place, I would probably say, well, I'm going to give you the actual answer. You can plunk around on your calculator if you like. What are we going to do? We're going to move that down. Ln 15. No, ln 12 divided by ln 1.5 equals. This is the actual answer, 14.12. So to 1 decimal place, it would be 14.1. But there's much better ways for us to do it. And again, don't worry about what I just did on the calculator. Let's take a look at a different method. I just realized up here that I have A and then C. Am I missing a B, or you just have 2 as well? Okay. What about graphically? Well, this is what I would have done in the previous questions. All we're going to do here is graph y1 equals y2 on our calculator and actually see where they intersect. So y1 is 12, y2 is in brackets 2/3 raised to in brackets x over 4. You need those brackets. Okay. So now we're going to use our knowledge of exponential functions. First of all, if y1 is 12, then in our window settings, we need to go up to at least 12. So for my y min, I'm going 0. For my y max, I'm going 15. When I look at the right-hand side of this, this is an exponential function with a base of 2/3. y2, we learned this on the first day, y2 will be a decreasing exponential function. So it will be entirely above the x-axis. Well, let's just hit graph at this point in time. See where we're at. There's 12. There's y2. Well, clearly they're going to intersect someplace way over on the left. So I'm going to go to my window settings and go from -25 to 10. That may not be enough. Oh, just barely. And that was just a fluke. I had no idea where it would be. Now I can go to my calculate menu, choose intersect, hit enter 3 times. With exponential functions, sometimes it takes a little bit longer. Anyway, we get about -24.5. That's the answer. try another one. So again, we're going left side equals right side. 75 raised to the exponent is a whole bunch of things being multiplied and subtracted, so we better put it in brackets. And then we also have 2.5 times 3 raised to the x. Now, you should have learned in the first lesson, even though I may not have told you this exactly, that when you have 2 to the x, it's an increasing function, but 3 to the x increases quicker, and 5 to the x increases quicker. Which means 75 as a base is going to be very, very steep. But both of these are going to have y-intercepts that are small. The y-intercept of the left side will be 1. The y-intercept of the right side will be 2.5. The y-intercept is always, as long as there are no vertical translations, the y-intercept, I'm lying a bit, is always going to be pretty close to a because there's a horizontal translation here. So my thought is, and I really don't remember from last semester, let's just go zoom standard, and see where we're at. There's that 75 to the 2x minus 3. There's the other one. You can see they're going to intersect someplace above. What I learned just in the past couple of years is you don't need to see the intersection point for your calculator to find it. As long as it's in the x domain that you've set up for your window settings, it will find it. We could change the y window setting to go up higher, but we don't need to. So if you go calc, intersect, hit enter 3 times. I think if you changed your window settings, it might find it quicker. But I get about 1.8. Any questions with B? All right, so I have tried in the past in this unit teaching a lesson on applications, and there's just too much. So on the first lesson, you did a bit of applications. Yesterday, we did a bit of applications. Today, we're going to continue with that. When you invest money, the interest is compounded. What does that mean? What is interest? I give my money to the bank, and my bank keeps my money. And for me allowing them to hold on to my money, they give me extra money from time to time, which is called interest. By the way, my money is not in the bank. The reason why they're able to make money is they loan it to you, and they charge you a higher interest rate than they give back to me. It's kind of a scam. It's kind of a swindle, actually. All they're doing is moving money around. Hope if your parents are bankers, I don't really mean that. Okay, I'm not saying they're swindlers. What does compound interest mean? When you calculate interest, let's just say I have a certain amount of interest, 5% that happens every year. At the end of the year, they take 5% of my money and they add it to my account. And then at the end of the next year, they take 5% again, but they take 5% of whatever the new balance is. So the amount that you're getting 5% of is growing each time, so the 5% is more each time. And that's what exponential growth is. So the next time they calculate interest, it's calculated using a larger amount. Well, that's exponential growth, and that means we can use this formula. Just to review this, y is the quantity that's growing. So you might want to make a note here that this is the money, or the amount of the money in exponential growth. T is the time. Well, that's pretty obvious. T stands for time. A is the initial amount. And you might want to put the word here, principal. There's two spellings of principal. I think it's this one for money, but I could be mistaken. And what principal means is the initial amount of money that you put into the account. B, of course, is the factor by which things change regularly, and we're going to have to talk extensively about that. And P is how long it takes for that factor to change. So P is really how much time for interest to be earned. So we're going to get to the specific example in a second, but if I told you you were getting interest annually, then P would be 1 year. If I told you you were getting interest twice a year, P would be half a year. P is how long it takes before you get interest. And we'll get to B. So, Jerry invests $10K in an account that pays 10% per annum. The word annum in math means annual. It comes from, I believe, a Latin term. Latin term is annum. So it's 8% per year. What does this mean? It means that if Jerry invests his money on January 1st, he puts $10,000 into this account. Then he's got $10,000 in the account until midnight on December 31st. And at that point in time, it goes up. And we're into the next year. So he gets at the end of the year 8%. Now, what I've already told you is that P is the length of time you have to wait to get interest. It's called P because it stands for period. We use P for period here, not K, which is what you use for trig. So P is 1 year. Now, I want to jump to the next question before we go on. The next question, it says Elaine invests $10,000 in an account. Elaine invests $10,000 in an account. And I'm going to adjust some things here. So if you're drawing this, don't draw it. It pays 8% per annum. So the bank puts up a big poster in the window, 8% per year. But that's not how they're going to calculate it. They're going to calculate it compounded quarterly. What does that mean? That means, first of all, I'm going to get rid of this thing. Well, I'm going to shorten it, and you'll see why in a bit. What this means is that for the entire year, she will get, in terms of a total of percentages, 8%, but it's compounded quarterly, which means it's split up into 4 pieces. Okay? And what that means is she's going to get 2% here, 2% here, 2% here, and 2% here. Which means, and I don't think you need to draw this, but what this means is that she will maintain $10,000 until the end of the first quarter, and then it goes up a bit. It will go up a bit here. This is not to scale. It will go up a bit here. And that's how the interest is going to be calculated. By the way, I will exaggerate something here for you. And this is highly exaggerated. The amount that it goes up each time is more than the amount it went up last time. Because at the end of the first quarter, she's going to get 2% of the 10,000, so she's going to have $10,200. Then she's going to get at the end of the next quarter 2% of $10,200, which is more than 10% of 10,000. Are you with me on that? So it's growing exponentially. And again, this is exaggerated, and you can see that that is exponential. Ian.
Why would we write it in a quarterly fashion when 8% every year is the same with the previous graph as well?
Because that's how banks advertise. They will say 8% per year, and then you will go in and you'll say, well, wait a minute, how are you compounding it? And Jerry's banker says to Jerry, we're compounding it annually, Jerry. Okay. Elaine's banker says we're compounding it quarterly. It's just the language that's used in finance. Okay. So when you look at Elaine's investment, if you only focus on this, this is a lie. She's not going to get 8% per year. She isn't. In terms of real money, it's not going to work out to 8%. And we'll see what it's going to work out to a little bit later. Okay. So what is P here? Well, P here is 0.25 years, a quarter of a year. P is the length of time it takes to earn interest. And I hope those graphics are helpful. Again, boy, this is really exaggerated, and especially if you compare it to Jerry's. Look how much Jerry earns. That's 8% of 10,000. There's no way that 2% of 10,000 is that big, but it's just a relative comparison. Okay, so let's go back to Jerry. We are going to use this formula. We want to determine how much interest is earned and how much is in the account after 14 years. So here's the formula we use. I want to impress on you, everybody, that these two things are variables, whereas A, B, and P are parameters. What's the big deal here? Well, the big deal is T and Y vary throughout Jerry's investment, but A is the same for every calculation, no matter what time we're using. B is the same. P is the same. So we've already established that P is 1. What is the base? Well, the base is 1.08. We've talked about this before. If you're earning 8% and you take 100%, which is what you start off with, and you add the 8% earned, you're going to have a value that's 108%, and this means divided by 100 in math. So this is 108 divided by 100, which gives you 1.08. 1.08 is what you multiply by every time you want to calculate the new balance. So B is 1.08. A, well, this is A. Right? Those are our parameters. A is 10,000, B is 1.08, P is 1. So when we put those three parameters, I don't have enough different colors here to highlight all of them, but this is a parameter that's going to go in, this is a parameter that's going to go in, this is a parameter that's going to go in. I guess I could have used green to have things match. This goes in as a parameter, so does this, and so does this. What does that give us? It gives us Y, the money, equals 10,000 times 1.08 raised to the T over 1. And we don't need to write over 1 there. You don't need to write it, but I'm just putting it. So how much is in the account after 14 years? Well, what this question is saying that? Right? It's saying when t is 14, what's p? So this is just a matter of running this through your calculator, everybody. I don't mean graphing it. I just mean taking 10,000 multiplied by 1.08 raised to the 14. And you get 29,371.94. So this is the answer to the first part of the question. Hang on to your question, Ian. That after 14 years of investment time, Jerry's account will have a value of $29,371.94. The second part of the question is how much interest was earned. And this isn't a complicated calculation. Jerry started off with $10,000 and he's got $29,000 now. The difference is the total interest that was earned, which is not going to be 8% because it's compounded. We don't even want to worry about what percent that really is. So this is the accumulated amount, and the interest will be equal to that accumulated amount minus 10,000, which will be 19,371.94. Ian.
When you figured out the amount in the account, how come that's P and not Y?
How come what?
How come on the graph it's P and not Y?
Oh. My brain slipped a gear. We're trying to find why. In some finance formulas, they don't use Y, they use a P for a very strange reason. So I apologize. That's why. Any other questions with that example? Okay. Let's talk about Elaine's investment now. So the first thing to note, let me make a list of the parameters, A, P, and B. The first thing to note is we've already established that P is 0.25 years, right? And this diagram, by the way, the diagram without the red stuff, this diagram is crucial to you understanding both what P and B are going to be equal to. Okay, so you have to, I'm not saying you have to draw it, but you have to imagine that that rectangle is a year, and compounded quarterly means you're going to have 4 chunks, which means it will be a quarter of a year. If it was compounded monthly, then P would be 1/12 of a year. Okay. The other thing that's very important about this formula is recognizing that B is not 1.08. It's 1.02. Because when the bank or the bank's computers calculate the interest payment, they're going to use 2%. So at every little quarter of the year, you're going to take your 100%, whatever you had at that point, add 2% to get 102%, and I'll do the same thing here. This is for Elaine's. It's 100% plus 2% gives you 102%. Again, percent means divided by 100. So this is where I'm getting 1.02 from. And, you know, I don't mean to, I wish we could just always just focus on math and not exams, but exams are a reality. If you're writing a written response, you have to explain this. You have to show this. It's obvious it's 1.02, but you have to justify it. And A is 10,000. So our equation will be y is equal to 10,000 times 1.02 raised to the time, which is a variable over 0.25. If we want to find out how much is in the account after 14 years, let's put 14 in for t and calculate y. Again, I just want to make sure that you understand. We're putting in a value for x and we're finding a value for y. So we're going to have 10,000 times 1.02 raised to, I'm going to need a set of brackets here because I'm raising it to a fraction, 14 divided by 0.25. You get $30,311. So this is the amount in the account, and the interest would be equal to $20,311.65 because she started off with 10,000. To how many of you is it obvious that she would get more money in the end because she's getting interest calculated more frequently? So it just after a quarter of a year, she's already increased the value. So the quicker you get interest, the more interest you'll get in the end. By the way, could you have, and some of you might prefer to do this, could you have done this? So I'm going to put an alternate equation for green. Could I have used 10,000 for A, 3 months for P, which is 12 months in a year, 3 months, 6 months, 9 months, 12 months, and 1.02? Yes, I could have done that. My equation would have been y equals 10,000 times 1.02 raised to the t over 3. But I wouldn't put 14 in for t. What would I put in for t? Ian? Not 14 times 3. T is going to be the total time that goes by. Shesmaida? 12 times 14. Because I've put P in months, I have to put in the number of months. And 12 times 14 is 168. I want you to notice something, though. And we don't need to do the whole calculation. Do me a favor and take 14 divided by 0.25. Just calculate that exponent. 14 divided by 0.25. 56. Which means Elaine gets interest 56 times. That's what's important. Do me a favor and take 168. 168, thank you, Shesmaida, divided by 3. You get 56, don't you? You better. What's important is 56 is how many times she gets that 2% interest. Okay, we have one question left. How long would it take each of their investments to reach 40,000? So what you have to solve for Jerry is this equation. And I've changed it to x because we're going to use our graphing calculator. And what we need to solve for Elaine's is 10,000 times 1.02 raised to the x over 0.25 equals 40,000. And we have to solve these graphically. You don't know how to solve these algebraically. So I'm going to enter in Jerry's 10,000 brackets 1.08 n bracket raised to the x. I'm going to enter in 40,000 as well. Clearly, I need to change my window settings to reflect that. So for my window settings, I'm going to go from 0 to 40,000. Well, to 45,000. For my x, which is time, I'm going to go from 0 to, well, we already know she hasn't hit 40,000, or he hasn't hit 40,000 after 14 years. Let's go 30 years. Just a number. I don't know what it's going to be. So let's go up to 30 years. There's her investment, his rather. All we have to do is find the intersection point. But there's something tricky about this. So for Jerry, and I've chosen this very carefully, what's the answer to the question? The question is, how long does it take for his investment to go past 40,000? Are we going to say 18 years? No, because he gets interest at the 18-year mark, and 18 is less than this number. So he has to wait to the end of year 19. We have to round up. So for Jerry, it's 19 years. Let's do Elaine's. So this was 1.02, and it was raised to, in brackets, x divided by 0.25. Did I get that right? Graph. Of course, it's going to happen sooner for her because compounded more frequently is better. So for Elaine, who can tell me what the correct answer is for Elaine? Jonathan? Yes, exactly. Her interest is being calculated every quarter of a year. So she gets interest at 17.5, which is a little bit less than 17.501. At 17.75, she's going to get more interest, and that will be what kicks her over that 40,000 point. So you would never answer this question by saying 17.5. You would have to round up to the nearest compounding period, which for Jerry is every year, for Elaine is every 3 months, or a quarter of a year. So it went a little bit longer. I apologize for that. You don't have a lot of questions to do here. Please make sure you know how to solve questions like 4 and 5. You do not need to check them using technology. For 6 and 7, do a couple on your calculator. Check to see if you can solve them graphically, which is a really nice thing to do. By the way, you could solve these graphically as well, if it's a multiple choice and you're just in a rush. And then there's some word problems here. I would say, 9 and 10 for sure would be my recommendation. So I would say make sure that you know how to do 4 and 5 for sure, and 9 and 10. Anything else is a bonus.